time. So let me welcome you here at the session 9A. My name is Jaromír, Hrad, as you can see in the description of my picture, I hope. And I'm coming from Czech Technical University in Prague, Faculty of Electrical Engineering. I have the honor to chair the session today. And as you know, it shall be focused on electricity and electrical engineering, renewable energy sources, and similar topics that are related to this area. As for the time scope, we have 7 presentations per 90 minutes. So typical length of your presentations shall not exceed 10 minutes, please. Be so kind, try to keep this time limit of 10 minutes, and possibly we can have some short discussion after every single presentation, let's say 2 or 3 minutes as the most, and we will see at the end if there is some time remaining so that we can discuss something in more detail. Well, I'm also going to be polite with you, and since I really am not sure how to pronounce most of the names of the presenters, I'd like to ask you to introduce yourself, including your affiliation and possibly any other details that may be of interest for the audience. So I'm just going to introduce the title of the paper, and please be so kind and introduce yourself. Although I know who is going to present each paper, I simply don't want to mutilate your names. Thank you. As for the technical details, you know that it is necessary to unmute your microphone before entering the presentation and the discussion. So please be sure that you have your microphone unmuted. I'll stay unmuted also for a while at the beginning of the presentation to make sure that you can get my feedback if something goes wrong. And I will then mute my microphone so that I don't disturb you. At the end of the presentation, as you could see in your instructions, it is necessary to stop sharing of your presentation so that the other presenters can continue and take the floor. So I hope that these technical details are clear. So since the time is limited, let me open the session, the technical program, and the first presentation, which is already prepared on the screen, shall be, as you can see, on a new protection philosophy for smart distribution networks. It's from Turkey, so please, the floor is yours, and we are waiting and looking forward to your message.
Okay, thank you, Mr. Chairman. Can you hear me?
Yes, it's okay, so please go ahead.
Okay, thank you all of you for attending my presentation. I am Abdulfetah from Istanbul Sabahattin Zai University, working as assistant professor. Originally, I am Ethiopian. I am working on smart grid. Specifically, I am specialized on smart grid protection. So I am going to present you my research work on a new protection philosophy for smart distribution network. The outline of my presentation will be, I briefly introduce what smart grid is, and I will focus on technical challenge introduced due to requirement of smart grid and specifically due to the integration of distributed generations. I will directly pass to the proposed method, which is adaptive technique actually, and I will suggest the implementation technique, and finally I will discuss the verification of the proposed method, and I will conclude my presentation. Smart grid, the need arises due to the environmental and other technical challenges like reliability. So in the last few decades, a lot of distributed energy resources are integrated into the grid. Most of these integrations happen into distribution networks. So the structure of the power grid is changed from radial energy transmission to bidirectional energy transmission, but the infrastructure is no more changed compared to the other technologies like information communication technology. And this integration of distributed generations and other further requirements, they motivated the development of the smart grid, which is the energy infrastructure with bidirectional flow of energy. The energy flows both from the source side as well as from the load side. And the ICT, the information communication technology, with its actually prevalent challenges. The ICT is already more developed sector compared to the power sector. So by doing so, the smart grid is intended to increase the safety, reliability, efficiency, the economic value, and environmentally clean use of the power grid. So this is the main idea of the smart grid. But compared to the other sectors, it's old sector, as I told you, and the structures of the grid are not ready for this modification, especially the smart distribution network. It's faced with a huge challenge compared with DG's integration. The main challenge faced with smart grid is the protection coordination. The protection systems, which were designed for classical power system, okay, like equipments, relays, fuses, and voltage transformers, circuit breakers, and the other stuffs, they are not suitable for the smart grid. Actually, the protections are characterized with selectivity, speed, sensitivity, reliability, and directionality. So there is a need to modify this protection technique. So to justify this one, we just studied a practical power plant. I personally involved in the design of this power plant. It is available in Antalya, 12 megawatt. It is connected to the distribution network. This is the DC interconnection, the DC circuit of the power plant, and it's connected to the distribution network at 30 kilovolt and to the utility further.
I'm sorry to disturb you, sorry to interrupt, but probably you are not sharing the correct window. If you are sharing the presentation window or the editor window, that makes a difference. So please make sure that we can see your presentation. We are still on the first slide. So if you are going forward in your presentation, then please reshare the different window.
Okay, can you see the changes now, please?
I can still see the first slide in the editing mode. So probably you should stop sharing and share the correct window once again. Yes, now it's there. Thank you.
So I don't repeat the previous one, and I just continue from where I stopped to save the time. So this is the Antalya solar power plant, which we used to take as a reference for to study the distributed generations integrations to the distribution network. So basically, this is connected to 33 kilovolt to the distribution network. These are the data for the DC and AC circuits of the power plant. Totally, you have 12 megawatt, and I personally involved in the design of the solar power plant. So we tried to investigate how the integration of this DG affect the protection of the distribution network, as well as the solar power plant when the already available protection techniques are used. So here, as you can see from this diagram, we applied a fault at a bus, which is nearer to 1 megawatt solar power plant. This is aggregated model. We use Dick Silent Power Factory to do so. So in this case, the fault current coming from the grid side is like 1.436 kilo ampere. And the other fault current is fed from the nearby distributed generation. So what happened in this case is actually the fault is identified by protection relay R3. And since the relay R2 is non-directional, still the fault current is sensed, and this relay R2 is operated wrongly because the original setting of this relay R2 is 20.017 ampere. So it's set to pick up value of 1.2 times the rated value. So there is a wrong operation of R2. So similar challenges happened when distributed generations are integrated into the grid. So there are also so many challenges reported in literature. So this is for a particular example. And another thing we observed in the same solar power plant is we tried to observe the fault current variation trends. In traditional power grid, the fault current increase when we go to the source side. Mostly the source is central power plant far away from the load. So there was a radial increase in fault current. But in case of integration of DGs, this is violated. As you can see in these two curves, we don't have only one directional increase of the current, we have two directional fault current, as you observe here. When you go to the solar power plant side, we have fault current still, which is also opposite to the traditional power grid. Even when we go to the network side, still there is increase, but the increase is not, it's not continuous. You know, you can see here some decrease. So this imposes a great challenge on traditional power protection. So we proposed adaptive way of protecting the grid. So adaptation is actually a natural process which is used by human beings as well as even by animals. So in this case, what happened basically in adaptive protection is operational parameters of protected systems are continuously monitored. So central or distributed units can be used. But this happened by analyzing actually the circuit breaker's status or whether the DGs are integrated or not, as we used in our case. Then a new protection settings are calculated based on this online and offline analysis, okay? Then by using efficient communication, which is actually assumed to be the part of the future smart grid, these new settings are distributed to the protection relays. So this is the technique we propose, even though there are so many techniques proposed in similar aspect by using adaptive. So here we use to monitor the status of circuit breakers as well as the circuit breakers which are used to connect the distributed generations. If there is any status change recognized, so the other setting calculations are followed. So this is a particular example. For example, we have condition A, condition B, condition C. From condition A to condition B, there is no any status change of circuit breakers, but from B to C, there is a status change. By using XOR logic, it can be easily recognized this status change. Then the other process will continue. So what we do is we calculate the short circuit and loading current, and we assign operating time multiplier setting of the relays at critical point. Then what we do is we calculate a new setting. Actually, in our proposed method, what makes it original is we don't need to devise a new device. Actually, we can use originally available intelligent in the device protection relays with minor modification on the computational capacity of those relays. Then we just do this one. We just initialize the setting for some particular relays, and these relays will communicate with other relays in their coordination order. So the architecture used is like hybrid between some central and distributed protection techniques. So we used actually the previously available well-known technique like IEC 2553 normal inverse curve, and it's also possible to use the same method for a definite invert time or other curves also, or for short circuit protections. So if I continue to the next thing, so this is the architecture we use. We have central controller, or it can be also used one distributed controller can be used, one of the relays can be used to handle this activity. This is a green broken line. They access the circuit breaker statuses and they recognize the status change. So some agents are used to calculate these statuses based on the previous example I showed you in the table. Then what will happen after we calculate the short circuit current and load flow at every place in the network? So these values are distributed to some peripheral relays. So these relays will have computational capacity. They will calculate their own setting, and they will send the time and time multiplier settings of their own to the next relay in their coordination order, so that they can calculate also their own protection setting. So this can be also realized by using IEC 61815 protocol, which is very common in substation and currently in all energy to communicate between different devices very fast. And in addition to that technique, to make our protection very fast, we added a follow me technique because the coordination happens in two directions. The relays in one branch will be coordinated with the same order of the relays in the same branch. So what will happen to protect one particular branch, the relay on the left side and on the right side, that means on the two ends, may have different time settings. So the relay with faster time setting, or the relay which recognizes the fault current earlier, has to send to the corresponding relay protecting the same branch so that they can operate faster than intended time. So there's also this great advantage of the method we proposed. Then we simulated this technique by using Dig Silent Power Factory. We programmed the agent techniques and the algorithms to calculate the fault current, load flow, as well as to recognize the network condition by using DPL, Dig Silent Programming Language, advantages in that aspect using Dig Silent Power Factory. So we checked whether this system or whether this technique works well. So we have observed that the time multiplier setting and operation times of the relays changing properly with each variation of solar power plant. We just initially integrated 4 megawatt and we increased by 1 megawatt to 15 megawatt. So at each stage, we have observed the relay setting are properly changed. And at one particular instant, we have seen the coordination curve among the relays. So they are properly coordinated. The curves are not overlapping with each other, so they are working properly. This is also for the other pass. There are four curves, as you can see. There is blue curve and green, red, and purple curves. For each pass, we simulated the fault current. I'm rushing maybe to conserve the time. Maybe it can be discussed later on. This is also for the other pass. The protection relays are observed to work properly without any overlapping of the curves. And we observed that the relay settings are changing properly for each integration of the digits. And we checked there is no wrong operation. For example, if we see setting one is designed for when there is only 3 megawatt integration. So there is no wrong operation when there is 3 megawatt, but if there is 4 megawatt of integration, if the setting is not changed to the second level, if we use the same setting number 1, so the relay will operate, this particular relay, RAD01 on our previous curve, will operate wrongly after 16.45 seconds. For further integration, if we increase further the digits, if the megawatt increased, even the protection relay will increase faster, but there is no actually fault current in the network. Similarly, if we see another condition, just to make it very clear, setting number 5 works properly, okay, until 8 megawatt is integrated. But if above 8 megawatt, this will trip wrongly. But setting number 5 cannot be used instead of setting number 4 because it can be oversized. There is a fault current and the fault current cannot be recognized. So by doing so, we verified our protection setting. And when I come to the conclusion, there is a great variation of fault current along the network due to the digits integration. This calls for new protection philosophy, which adapt to the fault current on condition of the network. The proposed method can vary with megawatt variation of the digits. And also, if there is any configuration change, can also adapt itself. It is adaptive and currently used intelligent electronic device, IEDs, can be used also with minor computational variation. To speed up the operation of the relays, we use the follow me technique so that the faster relay or the relay which recognizes the fault current earlier can send a signal to the corresponding relay and they can operate together to isolate the fault. So we use DPL, Dig Silent Programming Language, as well as Dig Silent Power Factory to simulate our network. So the coordination between the relays is verified in this aspect. As a future work, We are intending to change this one to the laboratory test by using hardware in the loop, and also finally to the site. We are planning to implement this one. Thank you for attending my presentation, and if you have any question, you are welcome.
Thank you very much. For the moment, I suggest not to go ahead with questions because we are not adhering to the time schedule. So I prefer to accumulate the possible questions to the end. For example, I also have a question concerning the communication techniques that you use or propose to use in your scheme. But for the moment, I'd like to thank you for your presentation and pass the word to the second presenter. So please now stop your sharing of your screen. And we will We will get the second one from the University of Shanghai, which is titled Evaluation of Wind Energy Accommodation based on two-stage robust optimization. Please, are you ready to share your screen? Yes, Mr. Tian. Please unmute your microphone and share your presentation. Yes. Okay, now we can see our desktop. But still we can't hear you, at least I can't. There can be something wrong with the microphone, although it is unmuted.
Ladies and gentlemen, it's an honor to have the opportunity to address such distinguished audience. I'm Kunpeng Tian. Today, I will briefly introduce my research evolution of wind energy accommodation based on two-stage robust optimization, and my supervisor is Professor Sun. This slide is about the outline of my presentation. There are totally 6 parts. The concept of power system dispatchability is described in section 2. The evaluation framework of wind energy accommodation is proposed in section 3. The solution methodologies are present in section 4. Numerical studies are conducted and simulation results are analyzed in section 5. Finally, conclusions are summarized in section 6. Background and motivation are given in this slide. Due to the external and internal driving factors, large-scale renewable energy is integrated into power system. The high penetration of renewable energy has become the development trend and important feature of the modern energy system. Renewable energy acts a pivotal part in the electric power industry. The production of wind power depends on the environment, which brings challenge to the economic dispatch of power system. For example, wind energy spillage and load shedding are widely concerned. The evaluation of wind energy accommodation can serve the economic dispatch, which is very important for the safe operation of power system. In this slide, based on the theory of pre-dispatch and redispatch, the concept of system dispatchability is proposed. We take a simple system, include 2 generators as an example to illustrate the process of power system pre-dispatch and redispatch as follows in Figure 1. The coordinate axis represents the power production of the generator. Rectangle H indicates the feasible region of the production power of 2 generators. PLP and PLR are their hand and real-time load demand, respective. Then LP and LR are the their hand and real-time dispatch scheme, which are given in equations 1 and 2. The pre-dispatch scheme needs to concrete because the information of their hand has prediction error. From the perspective of ramping, the relationship between of pre-dispatch scheme and redispatch is shown in equations 3 and 4. The shadow rectangle S represents the ramping capacity. which is the power system dispatchability and indicates the range of deviation from the predetermined operation point. The error of S is related to the pre-dispatch scheme, the ramping ability, and the response time. This manuscript proposes the evaluation framework and the metric indicates for window accommodation. The evaluation method is divided into processes. First, the pre-dispatch scheme is obtained by surveying the SCUC problem, and which is defined as the initial operation states of the electrical power system. The classical SCUC problem is simplified as equation 5 and 9, where equation 5 represents minimizing the start up and shutdown cost and the fail cost of TG. The binary variable X include the unit commitment, start-up state, and the shutdown state of TG. The decision variable Y indicates the dispatching decision, such as generator production power, transmission line power, phase angle. Equation 6 represents the minimum on-off time limits and the logical constraints of the start-up shutdown actions. Equation 7 represents the constraints of injection power balance, line transpower, and the phase angle of each bus. Equation 8 represents the constraint contain binary and continuous variable, including production power constraints and ramping constraints. Equation 9 represents the window power production constraints. Note that equation 5 and 9 are classical mixed integer linear programming, which can be directly processed by CPLX solver. Based on the day-hand scheme, the largest deviation of window power is calculated. The available band of window energy accommodation is obtained by surveying a two-stage robust optimization problem. The detailed evaluation model is given in 3B. The first stage is to determine the upper and lower bound of window envelope. The second stage is to determine the optimal redispatching scheme under the worst case window power realization. For any window power realization in the envelope band, window energy dispatch and load shedding should meet the constraints. Note that the model is a non-standard two-stage robust optimization problem because the uncertain set is the decision variable of the first stage instead of the predetermined boundary. Therefore, we need to decompose the uncertain set and the decision variable by equation 21 and the continuous variable V. V represents the ratio of the actual window power output to the largest operation range, and V is predetermined the uncertain set. The optimization aims to seek the bound of the envelope band such that there always find a practicable concretive action satisfying the constraints of window dispatch and load shedding. When any predetermined uncertain variable V, the standard two-stage robust optimization problem can be solved by Bender's algorithm. Meanwhile, we also notice that the super rare performance of CCG algorithm. This section looks at the methodology of two-stage robust optimization model. For the first stage, decision is predetermined. The second stage decision is recast as MLP by strong duality theory and disjunctive inequality. Specifically, the B-level optimization of the inner layer is transformed into a single layer optimization through the strong duality. However, the bilinear term in single layer optimization is transformed into MLP by disjunctive inequality. In summary, the three-level robust optimization is rewritten as a B-level optimization problem. The master problem determines the bound of the envelope band of the sub-problem determines the worst case of window power realization. The envelope of window power accommodation can be abandoned by Bender's algorithm in utterly solve the master problem and the sub-problem. The outline of Bender's decomposition algorithm is given in figure 2. A numerical example based on the modified IEEE 39 bus test the system are analyzed. The modified system contains 14 6 line and 10 generator, and the topology of system is given in figure 3. Detail the modified system contains a detailed parameter setting can be found in manuscript. The window farmer are integrated into the modified test at the nodes 3, 10, 15, 17, and 26 respective. The window farmer power production and the load demand profile are given in figure 4. The simulation program written by Jaromír and Cplex was run in MATLAB, and the average time of each calculation is about 300 seconds. The figure 5 and the figure 6 give a good insight into the ramping and the operation state of the thermal generator. The data in the figure 5 shows that the TG has stop and shutdown actions, in which the expensive generator is shut down to reduce the production cost of the power system. All TG are involved in the daily dispatch. The TG located on node 13, 13.3, 13.4, and 13.5 are always in the turn-on state, and another generator has stop and shutdown action. The thermal generator needs to provide upward ramping capacity to avoid load shedding. Besides, the thermal generator needs to provide downward ramping capacity to avoid window spillage. The result on this slide verify the fact window spillage and load shedding on the evaluable band. We design 4 cases according to the window spillage and load shedding. Case 1 is the most conservative. Case 2 is load shedding only. Case 3 is window spillage only. Case 4 is the most radical. The result of window power. The previous slide shows the development of window power. This slide details the result of case 4 in figure 9, in figure 8. Furthermore, the early window leakage or load shedding in case 4 in figure 9. As shown in figure 9, the total amount of window spillage and the load shedding, only window spillage and load shedding in case 4. Finally, we can get some conclusion. It is feasible to counterweight the deviation of window power by creating the pre-dispatch scheme, allowing certain window spillage or load shedding can greatly improve the ability to greater compute with window power deviation. The invaluable band of window power accommodation represents the maximum range of window power deviation for a system, which can provide worrying information for decision maker. Finally, thank you for listening.
Thank you also. As we are still slightly behind the schedule, I'd like to say just thank you for the moment, and we will see at the end of the session if there is some time left for the discussion. So please, gentlemen, record your possible questions and notes that you may have for this very presentation. And I'm going to pass the word right on to the third presenter from the University of Konya, Turkey. Please, it's about second order fast terminal sliding mode control for MPPT or PMSG-based wind energy conversion systems. So we're still remaining with the wind turbines. And please, if you are ready, I'd like Mr. Tian to stop sharing of his screen. and mute the microphone and pass the floor to the next presenter.
Can you hear me?
Yes, we can.
I don't share screen.
Okay.
Sorry, it is okay. Hi everyone. My name is Emre Hasan Dursun. I am from Turkey. I am a research assistant and PhD candidate at Konya Technical University in Konya, Turkey. I will talk about improvement of efficiency for WEX. My presentation topic is second order fast terminal sliding mode control for MPPT of PMSG-based wind energy conversion system. Content of presentation consists of 5 parts. The first one is abstract and introduction. The second one is PMSG-based WEX configuration. The later one is proposed MPPT controller, includes 2 parts, MPPT methods and controller designs. Other one is simulation studies and validations, includes 2 different wind speed scenario, and last one, conclusion of this paper. Abstract. This study proposed a new MPPT controller based on voltage mode second order fast terminal sliding mode control to obtain better performance in the power extraction from WEX. The major objective of this paper is the design of the second order fast terminal sliding mode controller. This proposed method can ensure the operation of the systems with higher efficiency and less steady state errors and voltage fluctuations. In this study, maximum power references are determined by mechanical sensorless MPPT methods, and WEX configuration consists of wind turbine, PMSG, uncontrolled rectifier, boost converter, and MPPT controller. Proposed method has not been performed before as a voltage regulator in such a this topology. For validation, the proposed controller has been validated for 2 different wind speed test scenario in MATLAB Simulink environment. Also, conventional sliding mode controller is created for comparison, and this controller performance is compared in the some criteria which are output power, MPPT efficiency, output voltage fluctuation, voltage error, and different performance indices. According to obtained results, the proposed method based MPPT controller achieves superior performance. Wind energy is special topics due to some reasons, because the world population is increasing day by day, and after that, technological developments constantly boost the country's energy demand. Conventional fuels-based energy generation raises serious concerns such as lack of research and global warming. In this point, renewable energy source is to be an effective solution for these problems. Therefore, the share of renewable energy source has been gaining momentum in recent years, especially in the last 10 years. Among them, renewable energies, one of the renewable energies, wind energy, is a clean and endless energy source, has one of the best application potential in the marketplace. Wind energy conversion system, in commercial application, the wind energy is called as wind energy conversion system, and so WEX are divided into 2 types because of constant speed and variable speed operation, and this one fixed speed WEX is generally cheaper and simpler design. On the other hand, variable speed WEX has been more preferred from small scale to large scale, and Higher power capture potential is also acquired by MPPT, different MPPT algorithms in these systems. In the VS configuration, various generators are employed. However, two types generators are usually in this industry, wind energy industry. These are double effect induction generators and permanent magnet synchronous generators. However, PMCGs have undergone significant development recently, so they have been preferred recently due to some advantages. These consist of efficiency, high power density, direct drive operation, gearless operation, simpler structure. So we use it in here. In industrial applications and research studies, various power conversion topologies are encountered. However, small and medium-sized applications are evaluated in terms of efficiency and cost. So we preferred following topologies in this study. In the according to wind energy, wind speed, considering wind speed is in a time varying form and includes high nonlinearity. For illustrating a view of the wind speed characteristic change can be these figures. For this reason, effective MPPT control schemas are required. These control schemas include MPPT search methods and controller designs. Controller designs will bring the generator to optimum operation point by switching the power converter. In the control of the WEGs, different methods have been used in literature. These methods are linear, intelligent, and nonlinear control methods. Linear control methods fail to provide sufficient performance, generally. On the other hand, intelligent control methods have some disadvantages, such as learning time, processing load, and prior knowledge requirement. And other side, wind nature and WEGs structure are nonlinear. So therefore, successful MPPT performance can be achieved by using the nonlinear methods. Sliding mode controller is a control technique, is a robust nonlinear control scheme and exhibits low sensitivity to disturbing effects and parametric changes. There are different types CMC in the literature. Conventional sliding mode controller, modified CMC, PID CMC, integral CMC, terminal CMC, fast terminal CMC. However, the other side, second order plus fast terminal sliding mode is combined technique, which is used in this paper. The authors this proposed methods as a voltage regulator for generating the control signal to bring the system to optimal value determined by MPPT. Thus, proposed methods has a better tracking performance and faster convergence. The designed wind energy conversion system configuration is shown as in here. Wind turbine, this is the wind turbine, PMCG generator, uncontrolled rectifier, boost converter, and load. Wind turbine is the mechanical part, the other side, electrical part. PMCG generator is direct drive and directly connected to the wind turbine shaft, and PMCG's output transferred to uncontrolled rectifier and the others. The captured mechanical power, when it's come to wind turbine characteristics, dynamics, the captured mechanical power equation can be seen as, and rho is air density, A is swept area, GP turbine coefficient, power coefficient, and wind speed. On the other hand, GP is the nonlinear function based on lambda and beta and some constant coefficient. After that, lambda is calculated with this equation, and radius, bleed radius, and omega m represents rotational speed of generator turbine shaft. From here, maximum mechanical power equation is defined as in here. PM maximum depends on Kp optimal and omega's cubes. During the operation, if MPPT is evaluated on the Lloyd side, namely for maximum electrical power consumption on the Lloyd, more accurate and effective results can be obtained rather than mechanical sides. Induced the electrical power equation on the Lloyd is in here, given in here, and the other side, induces back EMF of PMCG is defined as in here. One phase voltage equation of PMCG is defined given in here and given in here. And when mentioned, all over equations are ranging the output voltage of the rectifier is obtained as in here. As can be seen here, when the convergence at low power is ignored, linearity between DC voltage and omega m can be written as in here. Numerous researchers have been reported many different MPPT algorithms. For example, these different times is given in here, and they have, however, nonetheless, they have some advantages and disadvantages against the different methods. And after the some mathematical inference and replacements, PL max maximum on-load electrical power is based on KR optimal and DC voltage cubes. By the way, KR optimal can be acquired from simulation tests. Block diagram of proposed method-based MPPT controller for WEX is demonstrated in figure 2. The first one in here, second order fast terminal sliding mode consists of several design parts. The linear sliding surface design and the later fast terminal sliding mode controller manifold is created by in here. Others include some parametric coefficients and state equations. In this way, second order fast terminal controller, sliding mode controller generates control signal and it's transferred to WEX systems. Controller design steps. For these steps, the firstly dynamic of BC are obtained as in here, and boost converter circuit schema is given in here. The system variables to be controlled can be defined as in here, and then in the controller design, the first steps linear sliding surface is designed as in given in here. Then it is modified surface in here given in here. Later, fast terminal sliding mode manifold is designed with second order concept, and in this way convergence of the ST is guaranteed in finite time and reduced chattering. Thereafter, some replacing the state equations, it is synthesized as below. And from here, U control signal is arranged as the final equation for controlling to wind energy conservation system. Simulation studies and validations for obtaining maximum power from PMSG-based VEX and the performance of the voltage mode, second order sliding mode controller and conventional sliding mode control structure designed as a voltage regulator is tested and compared. Specific data for both PMSG and BC are given in here in this study. Test scenario one, for the test scenario one, wind speed profile is formed, wind speed profile having 6 and 12 meter per second range is formed as in figure 3. Change of the, also we can analyze this output extracted power which is shown in figure 4. It can be understood that a higher power extraction is obtained with less fluctuation and closer taking to optimal power. And then the change of boost converter output voltage transfer to load is indicated in figure 5. By the way, the other special graphics is the change of the boost converter output voltage error, namely on the load, which is presented in here figure, as can be seen, figure 6. As can be indicated in here, we can say that proposed method is closer to 0. It is desired. Obtained power data for each wind speed in this scenario are listed in table 2. The obtained, according to this table, it's clearly seen that proposed controller ensure a higher power and efficiency the other methods, and also efficiency up to 99.85. The other side, later one, voltage ripples and steady state errors are given in table 3, and we can infer from this table that they have been decreased by using proposed methods. It is desired. Another comparison in terms of performance indices, EIA, ECA, ETA, are given in table 4. Both data indicates the lowest value of the for other tables. Realistic scenario.
I'm really sorry, but I have to interrupt you at this moment because the time is pretty over and we also have to pass the floor to the remaining presenters. So really sorry for this. I have to cut it off because I simply expected you were coming to conclusions, but there's no time for this. So sorry, perhaps we'll have time to finalize this at the end. But now I have to pass the floor to Mr. Dobrucky from Žilina University of Technology. He's waiting for his input. So please, the floor is yours now. And please share the presentation with us. Yes, now we can see the editing window. I suggest sharing the presentation window instead. Yes, that's it. Thank you very much. And now the sound, please unmute your microphone. You're still muted. Still you are muted.
I hear.
Yeah, now it's okay. Thank you very much. Your floor is yours.
Thank you, Chairman. My name is Branislav Dobrucky. I am from University of Žilina, Slovak Republic. Our paper deals with simulation results and comparison of direct and indirect controlled matrix converter supplying 5-phase induction motor at first. Secondly, and mainly deals with experimentation of indirect controlled matrix converter supplying 5-phase resistive inductive load. The output phases of the converter load are connected in star, pentagon, or end pentacle configuration similar to induction motor phase windings. The article follows my previous contribution to improving the efficiency of the hybrid electric vehicles. The worked out results are compared through the output power performances of the individual configuration of the load phases. So this is the topics of my presentation. Is as usual introduction, basic connection of matrix converters, direct and indirect matrix converter simulation result, and then experimental verification with passive RL load, and the output power circumstances in the all three types of the load connections, and conclusion. So the first slide, you can see the connection of 5-phase, 3 to 5-phase matrix converter. This matrix scheme, this is the circuit scheme with the input in output, the synchronous generator and induction motor here. As a bidirectional switch are used, the blocking IGBT here. There are three types of winding connection of induction motor. At first, the star connection, pentagonal connection, and pentacle connection. You can see on this figure the star connection here, the pentagon connection here, dashed line, and the full line is the pentacle connection. So our load is also in this connection. The scheme for indirect controlled matrix converter is shown on these slides. So this is the first is the synchronous generator and fictitious DC link, not really fictitious DC link, and from DC link is this part of matrix converter indirect controlled to the induction motor or 5-phase inductive load. This is the simulation result for direct controlled matrix converter induction motor simulation. So you can see the star connection and pentacle connection. It's necessary to note that in the pentacle connection, the output voltage is approximately 2 times bigger than the in-star connection. It's important for our next explanation. Indirect controlled matrix converter with induction motor simulation results here. So this is similar to the previous one, star connection. This voltage, the red one is the current, of course, and the voltage is blue one, but the first harmonic is sinusoidal, but started from 0. The current is shifted by the cosine phi of this. Pentacle connection, the voltages in this connection is also nearly 2 times bigger than in star connection. And this is some theory how to control it, indirect controlled matrix converter. This is direct controlled, and this is derivation from indirect controlled matrix converter. Output voltages and voltages in fictitious DC link here is written. So the input currents can be calculated from these equations, and the voltages in alpha beta systems are calculated from this equation. So now I show you the experimental result from matrix converter supplying active and passive phase, 5-phase load system. So this is show the fictitious DC link. So it's not DC actually, but it's the like this. It looks like this. And now we can see the first star connection of the load. You can see the star connection here actually, and this is the result, measured result, and this is simulation result. So you can compare. This is good in comparing. Now this is the pentagon connection. So you can see the current and voltages. This is on this figure is the current, blue one, and violet is the current in the phase, and blue one is the current in the winding. So this is the voltage, yes, voltage on the winding. So this is simulation. This is an experimental validation, and so this is the similar figures, but the output load is connected in the pentacle connection. So the output current and output voltages are the nearly twice bigger than in star connection. It's in model, so this is just 50 volts maximum. Use this laboratory model, not really, because I'm sorry, we haven't so far the 5-phase motor. So we are our research is only for the resistive inductive load in this. This measurement of first harmonic, the first harmonic, the value is here. So this is first harmonic of the voltage, and this is derivation of the pentacle voltages between terminal A and C is the nearly twice bigger than voltages between 0 B and 0. This is derivation. So exactly it is 1.9 times bigger, the pentacle voltages. This is comparison between star, pentagon, and pentacle connection. This current, first harmonic of the current, first harmonic of the voltages, and this first harmonic of the active power here. And total active power, you can see that in pentacle connection we get the 7 much more bigger than the in star connection. So conclusion, direct and indirect matrix converter supply in 5-phase systems has been shown under active and passive RL load. Indirect controller supply was experimentally verified. The result of simulation and verification are in good agree. So this is the description of the. It was the star, pentagon, and pentacle connection in great detail in previous figure. In case of use of the 5-phase motoric load, its advantages will even greater due to independent control of the two induction motors by one converter, and the event of the single phase failure, still 80% of the performance remains for the driving. We have want to use for the hybrid electric vehicles. So for the driving is 80%. So it's all of my presentation. Thank you.
Thank you also. very much also for adhering to the schedule. Still, we are behind it slightly, so I apologize, gentlemen, but there's currently no time for questions, and I'm going to pass the word directly to the next presenter, who is Mr. Mohammed Arif from Islamabad, Pakistan, and the title of his presentation shall be Single Conversion Stage 3-port high-gain converter for photovoltaic integration with DC microgrid. So, are you ready, please, or is he here? Or I could see that he had some technical difficulties connecting to the room because I've admitted him for a couple of times, and I'm not sure if he's currently present or not. But he is surely here somewhere, perhaps not currently with us. Okay.
Okay.
So in such case, if you don't mind, I will dare to switch the order of the presentations. And since the sixth presenter is still not here, as announced, I will invite Mr. Dokur from Kulaksiz University in Turkey to be the next one if he is ready for the presentation. May I ask you, please?
Yes, I am
Thank you
ready,
very much.
Professor. Can
Thank
you hear me?
Yes, we can hear you.
Okay.
And yes, now it seems very well. We can see your desktop now.
Okay.
Yes, we can see the presentation. Very well. Please go ahead.
Okay. Hello, everyone. My name is Emre Dokur. I am an assistant professor at Electrical Electronics Engineering, Bilecik University, and also head of Energy Technology Application and Research Center, Bilecik University in Turkey. I am going to talk about the swarm decomposition technique based hybrid model for very short-term solar PV power generation forecast. My outline have main framework, and I will give a shortly introduction, and I am going to talk about the swarm decomposition technique and hybrid model results. Finally, I will talk the conclusion and discussion. My main work, my abstract is accurate predictions of solar photovoltaic power generation at different time horizon are essential for reliable operation of energy management systems. The output power of PV power plant is depending on nonlinear and intermediate environmental factors such as solar irradiance, wind speed, humidity, and etc. Intermittency and randomness of solar PV power affect precision of estimation. To address this challenge, in this paper, in this project, has studied a swarm decomposition technique based hybrid model as a novel approach for very short-term solar PV power generation forecast. The original contribution of the study is to investigate use of swarm decomposition technique for solar data forecast. The solar PV power generation data with hourly resolution obtained from the field, where is located in Turkey, solar power PV power plant, is used to develop and validate the forecast. As you seen in the figure, the flow chart of the study, I will give a detail about the flow chart in the other slides. Rising energy demand and its related environmental impact increase the use of the renewable energy resources in generation rapidly. PV panels have recently become one of the fastest growing renewable power generation techniques. As you know, the renewable energy resources are nonlinear structure and highly depending on geographical locations and weather conditions. So integration of the large-scale photovoltaic power system into interconnected systems is becoming a major challenge. So the solar and also wind power forecasting is important for the power systems. The generation schedule should be planned for very short-term and long-term power system operation in order to ensure reliable operation and economic dispatch of modern power system. The researcher have proposed lots of methods with various time horizon for modeling and forecasting of PV power, such as artificial intelligence technique, deep learning, hybrid models. Today I am going to hybrid models especially, and as you've seen in the figure, the forecasting horizon and related application in this figure. Swarm decomposition technique, a novel signal analysis called the swarm decomposition technique has been proposed by Apostolidis and Hagiotolitis. Swarm decomposition based on the biological swarm rules is a preprocessing method for non-stationary signal. The most important step of the swarm decomposition is swarm filtering that operates with the swarm prey hunting approach and also produce escalatory components from an element input data. As you've seen in the presentation, the pseudocode given in this section, there are lots of parameters in this technique, such as input signal, swarm hunting parameters, and members, control flexibility of swarm, and threshold and output of swarm filtering. As you've seen in the figure, and I am going to talk about especially, although this pre-processing method has been used for the decomposition of many biomedical signals normally and different non-stationary signal research, it has been applied to solar data for the first time in the study. In the study, the real solar data, power output data obtained from the solar power plant for the pre-processing and the composite sublayer by using the swarm decomposition. Real solar PV power output time series data of solar power plant were decomposed into 5 sub-series by CVD. Particularly high frequency component which have changed in solar power output during the Klutli periods have been detected in this sub-series. As you've seen in the figure, the solar data and reconstructed solar data after the pre-processing is given here, and time domain and frequency domain figures. And I am going to talk about the hybrid approach, and as you've seen in the figure, the figure shows the sample hourly power and energy outputs, the clear sky data, but I will use the closely and rainy periods. As you've seen in the figure, you can see the flow chart. The flow chart of the study is given in here. Firstly, the data was collected from the solar power plant and it is normalized before the pre-processing step. Sub-series of solar data were obtained using the swarm decomposition technique. For each sub-series, feed-forward neural network model was established and outputs were obtained. All separate forecasting result achieved by each sub-series models were collected to obtain the value of final estimation. I used the sliding window technique for the forecasting method. Also, the hybrid approach was run 10 times independently, and the performance results are evaluated, the performance metrics. As you see in the equation, some error metrics such as root mean square error, mean square error, were used to evaluate the forecasting performance of the proposed methods. Also, you see the sample results of the composite signal 1 forecasting and performance criteria of the study. The figure shows the decomposite signal 1 forecasting results and performance metrics in here statistically. Also, finally, I am going to talk about the hybrid approach results. The performance of the proposed hybrid approach is higher in closely periods. According to performance metric results in here, in table, there is significant improvement in error measurement compared to other forecast model in selected closely case. In this project, a novel PV forecasting model based on the swarm decomposition and Pittsburgh-NL network is given to forecast the power output of a PV system. The results were obtained by applying separate estimation model for all sub-series. The simulation results show that compared to other PV forecasting method without the processing approach, the proposed PV power forecasting model can significantly improve the forecasting performance in closely periods. Thank you for your attention.
Thank you also for being on time and for this interesting introduction. Perhaps now it seems that Mr. Arif is with us or not. I'm not sure. I will check. So should be here. So let us give the floor to him, and hopefully we will have some time for questions if the organizers will allow us to do so. So thank you for the moment, Mr. Dokur, and please, Mr. Arif, could you share your presentation? Which will be on single conversion stage, 3-port, high-gain converter for photovoltaic integration with DC microgrid. So we still are with wind turbines or solar systems. Please unmute your microphone and share the presentation. Now we should hear you. What we can hear actually is some noise in the background. Yes, the screen is becoming to be shared. Yeah, now we can see your PowerPoint editing window. So if you'd like to show us the presentation, it would be better to stop or like this. Okay. Yes, now we are sharing. We can see it. We can see the presentation window now. So please, the floor is yours.
Thank you, Chair. I am Mohammed Arif from Comsat University, Islamabad, Abdela campus. My presentation title is Single Conversion Stage 3-port High Gain Converter for PV Integration with DC Microgrid. Presentation outline is motivation, introduction, proposed topology. I will explain the proposed topology, operational modes, the mathematical modeling and design consideration, results and discussion, and at the end we will conclude our overall work. Motivation. The figure shows the future DC microgrid where, as we know that the penetration of renewable energy increases day by day, and the significance of the DC microgrid increases, especially in the low voltage DC distribution and generation. With the increased penetration of renewable energy resources, especially the PV system increases day by day. But there are some issues with the PV system for the integration of with the integration to the DC microgrid. The first one is the low voltage generation, and the second is the intermittent nature of the PV system. But these issues can be overcome by using for the low voltage generation, we can use high voltage, high gain conversion system, high gain power converter, And for the intermittent nature of the PV system, we can use the storage devices. So for this, in recent times, the researchers has developed many converters uh, for this kind of system. But there are some issues that the researchers has the topologies which has more number of components or the multiple stages to convert that low voltage generated by the PV system to the high gain compatible with the DC bus system, which is the standard like 380 volt by using emergent lines, which is the standard DC bus voltage. With the with low voltage generation. So the battery port provides the stability to cope the intermittent nature of the PV system. So the researchers in recent time researchers has developed many converters, but those converters has the limitation of the high gain by using the more number of devices. Those converter has has multiple conversion stages, which increases the size of the converter, and also the decreases and also decreases the efficiency of the converter. So for this, our objective is to develop a converter that not only cope these limitations in the conventional PV integration system with the DC microgrid, but also to reduce the conversion stages and also the passive devices count in the design of the power converter. So our objective is to use the PV and battery system to integrate it with the DC microgrid. So for this, we introduce a 3-port converter where we have a PV system and a battery system integrated with the DC microgrid. So converter has the following features. It has a 3-port bidirectional power flow capability, a high gain storage capability, simple structure, almost ZVS, zero voltage switching is achieved without using extra circuitry. So the converter is based on the availability of the PV power and the battery charge and discharge. The operation of the converter is divided in SISO, which is the single input, single output mode, DISO, double input, single output mode, and the SIDO, single input, double output mode of operation. Here we have the proposed topology. This is the input port for the PV system. We have a battery port for the battery. We have a coupled inductor. The only for the high gain feature, along with the switch capacitor, we have active clamp circuit to reduce the voltage stress on the main switch, and we have low port. The operation, the converter has only single conversion stage. So the conversion topology in all of the modes, in SISO, DISO, and SIDO mode, the some part of the circuit will active. For example, in SISO mode, this is the active circuit part and the current flow path, which will be active for the whole operation during the power transfer from PV to main DC bus. And also for the SISO mode, we have 3 mode of operation, like power transfer in single input, single output mode of operation from battery to the load. The figure 3B shows the current flow and the active part of the converter circuit. In figure 3, in buck mode, when the battery is charged from the DC link, is shown in figure 3C. And for the DISO mode of operation, the active circuit and current flow path of the circuit is shown in figure 3D, where both PV and battery provides power to the load. Keep in mind, the mode of operation depend on the availability of the power from the PV and the charge and discharge of the battery, and also the nature of the load. Either it is a light load or a heavy load and so on. So we can switch based on these conditions into different mode of operation. So the last mode of operation is the single input double output mode, where we have the only source, we have enough power at PV port to both charge and serve the load. So this circuit shows, figure 3E shows the active part of the circuit, which is used for the SIDO mode of operation, single input double output, where the only input is the PV port and the output is is the battery port and the DC link capacitor. So for this, we have developed a complete mathematical modeling and analysis is explained in the paper. We just write the key conversion, the conversion equation in each and every mode of operation. For SISO mode, we have 3 operations. When the power delivered from PV to the DC port, we have the conversion ratio of this, and we have the conversion ratio of this in 2 when the power is transferred from the battery to the main DC link, and in third mode of SISO operation, where we have the power transfer from DC link to charge the battery at the input side. So this is the buck operation, and other two are the boost operation. For the DISO mode of operation, we have these relationship, and also for the SIDO mode of operation, we have this one. So as we know that, as you see in the topology, we have only one magnetic element, which is for the main part of the circuit, which is the coupled inductor. So for the design consideration of each and every component is explained in detail in the article. But here I just show you the crisp of the coupled inductor design flow, where we have the design specification, and then based on the power output power, we select the core, and then we calculate the inductance, and then the loss calculation, wire and flux density calculations are done, and if it is true, then we calculate the bobbin fit calculations, and then we develop and test inductor. If it's not true, then we go back to the to this loop, and also in this loop. We design the switches according to our requirement. As we develop a 500 watt prototype, we choose the switches and the diodes accordingly. As we are using active clamp circuits, and some of the switches we are using with low voltage stress, and we are using the diodes, fast recovery and ultra fast diodes. We have the design criteria for the capacitor selection. We have 3 capacitors. One is used for the load capacitor, and we have a switch capacitor, and we have the active clamp capacitor. So these figure 5, 6, and 7 shows the results, simulation results modeled in Plex simulation results in SISO, DISO, and SIDO mode respectively. So these results are in close proximity with the theoretical analysis. Figure 8 shows the hardware prototype and laboratory photograph of our system. Here, this is the 500 watt hardware prototype of the converter. These are the MOSFETs. This is the controller slot. We are using TMS F28379D. This is the inductor. This is the coupled inductor, and we have 2 ports. One is for the battery, and other is the PV port, and we have the output port over here. And this is our experimental desk, which is the in our laboratory. So figure 9 shows the SISO mode of results in experimental results in SISO mode of operation. In this mode, the active switch is S1. So we have the input voltage of 48 volt at PV system for the validation of for the operational validation of the converter, and we have the duty cycle for that switch is 0.5, and we have voltage stress of 96 volt, and this shows there are some ripples and the VDS voltage. This is due to the leakage inductance of the copper inductor, and we calculated on the scope, and which is around means by calculating the resonant frequency of the these ripples, and then from there we calculate the leakage inductance. These are the experimental results in DISO mode, and the active switches are the S1 and S2, and the rest of the results are same because the main part of the converter is common in all mode of operation. But keep in mind the converter has only single conversion stage. So these are the experimental results in SIDO mode. So we have the active switch again S1 and S3, and again these results are in close relation with the simulation results as we shown previously. So at the end we compare our proposed converter with the state-of-the-art converter in the literature in SISO mode of operation. As we know that we have comparison in terms of the reduced device count and in the high gain feature. So conventional boost converter has these parameters: switches, diodes, capacitors, inductors, and the converging gain. And the reference article in 13 has this convergent gain, and proposed converter has this one. Proposed converter has highest gain as compared to these converters, although reference 13 has minimum device count in terms as we are using the switch capacitor to elevate the voltage at the output of the converter, but the gain of this converter is low than the proposed converter. Figure 13 shows the gain comparison of the proposed converter with the state of the with the cited and the selected articles are the work presented in 13, 17 and conventional boost converter. So here we can see that the the proposed converter and the reference the work presented in the article 17 are in as the duty cycle increases, the almost gain is same, but we can see the clear difference in the device count. The converter proposed in 17 and as we has proposed in this work. So this is the conclusion. In this work, we proposed a three-port converter which has the bi-directional power flow capability. The leakage inductance is achieved by using without using extra circuitry, and we are using the leakage inductance of the coupled inductor to achieve ZVS. Converter has an efficiency of 96% in SISO mode of operation. Comparatively with the paper cited in this article, the converter has less number of device count. We are using the active clamp and switch capacitor technique to elevate the voltage at the output side. And at the end, the converter is the operation of the converter is explained in SISO, DISO, and SIDO mode of operation. As we discussed, is single input, single output, double input, single output, and single input, double output mode of operation. Moreover, nowadays we are working on the control and the energy management between different ports of the converter is will be discussed in the future articles and may be proposed in the future work of this research. Thank you very much for your time and attention.
Thank you also. Gentlemen, we are finished with all the presentations that have been represented today, And I just would like to ask the organizer if we have some time for discussion or questions and answers, because I have eliminated these during the course of the session because we weren't sure about the adherence to the time schedule. So please, Darius, are we allowed to have some?
I think yes, you have. I think discussion is very welcome.
Thank you very much.
It's up to you to manage time, and maybe I just would like to thank you to all participants, to all presenters, virtual participants, because form of the conference is a bit different, but I'm really glad that almost all participants made their presentations, and I hope to meet you probably next time somewhere face to face. So please continue this discussion, and I will be somewhere around you. Thank you, Mr. Chairman.
Thank you very much. Also, I'd like to apologize once again to the last presenters from the Institute of Fuzhou, China, because the paper titled "A Novel Pre-Synchronization Control for Grid Connection of Virtual Synchronous Generator" has not been presented, probably because of some personal reasons. So just to recap, we have had 6 presentations, and now I'd like to use my right to ask just 2 simple questions, which are focused on the first and on the third presentation. Perhaps the questions are a bit silly, but it is because of my primary area of interest. So I'd like to ask Mr. Shobole about your design, because you have mentioned that the communication uses some efficient communication means to send the warnings and information inside the design system. So could you please elaborate on this efficient communication? What technologies or what type of communication shall be used?
Okay. Thank you for your question. It's an interesting question. First, I say that the communication infrastructure is one of the main important components of the smart grid, because you cannot realize smart grid without efficient communication infrastructure. Specifically, when we come to the substations, or maybe distribution substations, previously wired communication infrastructures were used. It can be copper wire. Later times, fiber optics were used. Now, due to the development of IEC 61815 protocol, this protocol can transmit data in real time over Ethernet. So the current devices, intelligent end devices, for example, the protection relays, they are implementing this protocol, IEC 61815 protocol. So it is easy to exchange data. For example, the circuit breaker status data can be represented in binary, and it can be sent over Ethernet. When we come to the, if you are asking about the architecture of the communication, since we use now this protocol, IEC 61815 protocol, we are not using the previous methods like master-slave. So the devices, they are configured initially which device will communicate with which one based on IEC 61815 protocol. So based on publish and subscribe method, for example, for if they use GOOS methods, generic object-oriented communication, so they can communicate by using this protocol. So it is easy to implement my method by using this protocol. But in actual simulation verification, I just used Dig Silent programming language and the Dig Silent Power Factory. So there is no any requirement for me during the simulation to implement this communication. But in practical application, I will do that one. Thank you. If I answered your question.
Thank you very much. How about considering, for example, power line communication in order not to have to implement any extra network to the existing infrastructure in parallel? How about PLC?
It's interesting question. Among the communication infrastructures, especially in substations, we need more reliable communication infrastructures. Even if we have access to power line carrier communications, we suggest, in case of especially protection signals are very sensitive, very important signals. So we suggest to use fiber optic Ethernet even. We suggest to use fiber optic Ethernet because the power line carrier communication is very prone to noise signals. So the signals which are used for protection, they must be very accurate. So we don't suggest to use power line communication. Thank you.
Thank you. Thank you very much. So, gentlemen, this was my question concerning the first presentation. Is there anyone else who would like to ask Mr. Shobole about anything concerning his results? Doesn't seem so. How about the second presentation? Thank you. Thank you. How about the second presentation given by the colleagues from the University of Shanghai? Any questions specifically? Well, doesn't seem so. As I've hinted a while before, I'd like to ask Mr. Dursun about, again, just a tiny detail. It's rather a note or just a bone note than a question, but you spoke about endless energy, which is represented by the wind. Well, can you imagine a situation when wind wouldn't be available? Or, you know what I mean? I'm just trying to hint about the situations, for example, in the coast of a seaside, when the situation is rapidly changing from hour to hour, and the wind either blows or not, and both situations can be a problem. So how about this consideration about the endless energy consisted by wind? What is your opinion about that, Mr. Dursun, sorry. If you're still here. I can't see the colleague here. So sorry, we will have to skip this. And how about the rest of the presentations? So this was from Jelena, from Bilecik, and from Islamabad. Any specific questions or notes, colleagues, please? The floor is open. Well, Darius, do we have, please, some inputs from YouTube channel? Well, it doesn't seem so. So in such case, I'd like to say thank you once again to everyone who has participated actively in this session. Thank you the more that you have agreed to participate in this, let's say, substitutional form of presentation and conference in this difficult time for everyone. So let's hope that the situation around the globe will be more relaxed in a couple of weeks. And I also like to wish you all the best, good health, and express my hope that we will have a chance to meet in person on some more pleasant occasion. Thank you very much. I'm officially concluding the session. Have a nice afternoon, or depending on your time zone. Thank you.
Thank you.
Thank you. Thank you.